In this lecture, we're going to talk about addition of HBr to an alkene in the presence of peroxide. Typically, when you add HBr to an alkene, you end up with the Markovnikov product, where the bromine goes to the more substituted position. Let's briefly review this. Remember, our electrons would go to the hydrogen-bromine bond would break. We'd get a carbocation intermediate, and then Br minus would come in to give the product. So this is the Markovnikov product. Where the bromine is added to the more substituted position. However, when we add HBr to 1-butene in the presence of a little peroxide, we see instead the anti-Markovnikov product. You can see here that the bromine is adding to the less substituted side of the alkene. This reaction goes through a radical mechanism, and we'll go through it so you can see why we get that bromine adding to the least substituted side. You can see here another example of an alkene reacting with HBr in the presence of peroxides. And again, you see that we get the anti-Markovnikov addition of HBr. A common peroxide that you might see is hydrogen peroxide, HOOH. You might also see benzoyl peroxide. Here's a little bit more detail on the mechanism. Our peroxide source, which we talked about, can be something like hydrogen peroxide, undergoes homolytic cleavage or homolysis to form 2 radical species. Then one of the new radical species reacts with HBr in an SH2 reaction to form bromine radical. Next, we have radical addition to an alkene, which gives us the most stable radical. This radical that we formed is secondary as opposed to a possible primary radical. Finally, another SH2 step happens where the radical that we just formed reacts with HBr to give our product and regenerate bromine radical. This slide gives us more detail into why we get the anti-Markovnikov product versus the Markovnikov product. In our radical addition to an alkene, if bromine radical reacts and adds to the left side, we get secondary radical, and if it reacts with the right side, you get a primary radical. The secondary radical is much more stable than the primary radical, so that's why it's formed. Briefly, here's what formation of the primary radical would look like. And that radical would just be too unstable to form. In HBr addition to an alkene, in the presence of peroxides, we see a mixture of enantiomers because there's no selectivity in this reaction. The alkene can be attacked by bromine radical either from the top or from the bottom, and in the second step where you have a reaction of a radical, it can also be attacked both from the top and from the bottom. Once bromine radical is formed, it can react with a double bond to form either this radical on the left or this radical on the right. So you see in that both of these cases we have a secondary radical, and the one that's preferred is the one that's stabilized by the benzene ring. So this is the one that leads to the products shown. This picture shows the radical step where the radical is reacting with HBr, and you can see that the radical is hanging out in this empty p orbital, and it can react with HBr either on the top face or the bottom face. So there's no stereochemistry in this step, and there's also no stereochemistry in the first step where we're reacting the alkene with bromine radical. Just to quickly do one more example, if we had something like this and reacted with HBr in the presence of peroxides, we'd end up with 4 possible products, because now we have a new stereocenter here and here.